Thank you again. Well, welcome back here. We're happy to have you with us, joining us this evening for our SKYWARN Storm Spotter training. My name is Dave Purcell. I'm the coordinator for Steele County SKYWARN. I started to say earlier, I've been working in and around severe weather since 1982. When I was participating, I was working at a radio station in northwest Iowa. We had a 9-county spotter network and our own weather radar. Folks at the TV station would actually be calling us for information.
And my name is Jerry Iberson. I'm an instructor here with Steele County SKYWARN. I've been with SKYWARN since 2009. Had some interesting experiences over the years. When I retired, yes, in 2009, became a professional volunteer and got more involved with SKYWARN. One of my official positions right now is in emergency management for the city of Ellendale.
And with that, let's get into the training.
Sounds good.
So we want to understand what the role of storm spotters actually is and why it's so important, why storm spotters are important. Well, if you're up in Chanhassen and you're looking down in this direction to see what's going on, the radar, great tool that you have, can only see those portions of the storm above about 5,000 feet. Fortunately, some of the most important parts of what's going on is down in the bottom, and that's what spotters are for. We can give the ground truth to what's happening and what they think is happening in the upper portions of the storm.
Now, when the National Weather Service up in Chanhassen, when they look at their radar, this is what they see. Now, what they really like is spotters on the ground. What we can see when we're out in the country, we can report what's actually happening.
The other role that storm spotters have, people are far more likely to actually take action if they perceive a threat as being real. And spotter reports add credibility to those warnings, as opposed to seeing a radar-indicated threat. To actually say a spotter has actually seen what's going on adds credibility, and people are more likely to take action.
And the role of storm spotters with the National Weather Service. It's all part of the decision-making process when the Weather Service wants to issue a warning. Some of the things they look at are the radar signatures, the storm environment, surface observations, and of course the spotter reports from the people out in the field. In addition to satellite trends and climatology, the spotters are a very important part of when warnings are issued.
Let's look at some of the places we get information from the National Weather Service to help us understand what those threats are going to look like throughout the day. One of the places most of us as spotters start is at the SPC, or the Storm Prediction Center. They offer the convective outlooks, which give you a look into the risk for severe weather across the country as far out as about 7 days in advance. Address for that is www.spc.noaa.gov. And they give that outlook, convective outlook, to show us what those threats are going to be on day 1, day 2, day 3, and then a big chunk in the spread out days after that.
Now for accuracy, sorry Dave. This is September 20th, 2018. This is what the predicted storm area was. Right here is what actually happened. The red dots were actually tornadoes, with the blue dots were high winds. So their forecasting was indeed very effective.
Now, the SPC convective outlooks, they talk about different threat levels here. And that range all the way from just regular garden variety thunderstorms, all the way up through marginal, slight, enhanced, moderate risk, and high risk. Now, it's very unlikely or very rare that you'll actually have high risk this far north, but it does occasionally happen.
Looking at the SPC convective outlooks, this again is for that date in 2018, showing the green, the brown, and the yellow. The crosshatched area shows the severity, which shows chance of hail over 2 inches and increased tornado threats of F2 or greater.
This is the tornado outlook. This is the wind outlook for that same day. And this would be the hail outlook for that same day. Again, they've shown to be very, very accurate. Where do you get all this information at? National Weather Service website, weather.gov/Twin Cities, gives you that information for our area. You can get an hourly forecast for your specific city or zip code up in the upper left-hand corner of that page. My favorite portion of that website is the weather story for the day, which we usually carry forward to our Facebook page as well.
And there's the weather story. The weather story is issued normally twice a day at the National Weather Service out of Chanhassen for our particular area. It shows the main weather story, the main thing that's going to be happening. This one was for the tornado potential of September 2018.
Now, if you're looking to understand a little more about why they made particular forecasts, great place to start with that is going to be the area forecast discussion. And again, you can find this on the National Weather Service website, weather.gov/Twin Cities. Look under forecast and forecast discussion. It's a much, much lengthier description of what's going on and what was in their mind as they were writing the forecast.
This is the interesting part, the hazardous weather outlook. It shows the different color sections, according to the state. This particular one was for severe cold, sleet, and snow with red, orange, and yellow. And then we have the stop and go light system for the different days, for the current day on and for the next 7 days. It shows the different threats of tornado. And down here, we're down into the excessive cold, which was affecting us that particular day, again with the color codes from green, yellow, brown, down to purple. Also an important part of this is the spotter statement. In this particular day, it will tell you if spotters are actually going to be needed or not, or it will tell you no spotter activity is anticipated.
Now, this is kind of a busy page. There's a lot of great information on it. But if you're having troubles deciphering it, one of the things you might want to do is stop over to our website, steelecounty.skywarn.org, and look for our weather dashboard. It's a nice collection of great forecast information to show you what's going on and what is likely to go on throughout the rest of the day.
And actually, that is what I have as my home page on my computer when I start it up. Every morning, that's the first thing I will check.
Great idea. Another piece of information that you can find from the Storm Prediction Center, which is a great tool, is the mesoscale discussions. Now, these don't always happen if there's nothing going on, but they're issued several hours in advance of any significant event. At least that's the plan. They can also be used as a progress report to show what's happening and whether that's lining up with what their forecast actually was. They serve as a heads up for severe tornadoes and severe thunderstorm watch might possibly be imminent. And speaking of watches,
here we get into the severe weather watches and severe weather warnings. What's the difference? A weather watch is issued when the weather is favorable for severe weather to happen. It's usually issued 1 to 3 hours in advance, sometimes even before storms develop. The particular radar screen in front of us right now is again from September 2018. The storms are over on the Dakota border when they started issuing the warnings in southern Minnesota. It's a sign that storm spotters need to get ready.
By comparison, a severe weather warning or a tornado warning indicates that severe weather is imminent or occurring right now. Now, these used to be done by counties, but quite a while back here, they've actually switched over to polygon-based warnings. That means some of the larger counties in northern Minnesota cover huge amounts of the state, and so therefore, a polygon is far more accurate. It tells you where those threats are. And it gives you an idea so that they can warn anyone of the alert anyone of the warning that is at risk. Important point about this stuff, they need our reports because that helps to validate those warnings even after they've been made.
The severe weather warnings are often impact-based. They will tell us what the hazards are going to be, whether it's hail, strong winds, heavy rainfall. Also, they'll specify down here 2-inch hail, for example, 60-mile-an-hour winds. This is what they anticipate when they issue a severe weather warning.
So how do you find out about all of these warnings? And with that, there's a plethora of a way. They wanted to make sure there wasn't just one way to receive warnings. And so therefore, they've got all sorts of various choices here. And what we look at here, there's TV, there's radio, there's the various widgets and weather apps, NOAA weather radio. Let's dig into a few of those, but it looks like we've got a question.
One question that's came up, how many minutes notice are we behind when it first comes to Chanhassen?
Could you be a little more specific with that?
As far as when Chanhassen is notified, how long does it take for that warning to come out?
When Chanhassen is, if they actually are the ones that are making that warning decision, when they click on send, it goes out, and it goes out simultaneously in all of those different channels at the same time. Now, as far as the warning decision, when did they make that decision based on that information? They're looking at things that we're going to be discussing later here, but they're making those decisions based on what observations we're seeing from spotters as well as what they're seeing from radar. Hopefully, if it's not quite what we're asking, give us another, expand on the question a little bit. We'll be happy to try to answer it. Let's dig into some of those dissemination methods.
Okay, the wireless emergency alerts. Those are, again, based on the polygon and the mobile cellular towers inside or covering the polygon. So anything that is connected to those cellular towers will receive the warning. It's become a very important and very effective method of notifying people of when severe weather is occurring. Also, if you may be in the polygon, but if you're not connected to, or if you're connected to a tower outside of it, you may not get the message.
And that explains why sometimes people don't get messages when other people right next to them do. Also remember that there's multiple cellular carriers, and your tower might not be located in the same place that the polygon's at.
Then we come to the NOAA weather radio. It's a constant weather forecast with stations located all around the state of Minnesota, or the United States actually. So your weather radio is specified by county and weather type as to when you want the alerts to go off. If you just want a weather forecast, you can touch the button and get the current weather conditions and forecast. When the alerts come out, an alarm will go off on the radio and give you the warnings as they pop up. These radios are available at major suppliers, box stores, or online for between $20 and $40.
Now we're into my favorite part of the program. We're looking at step-by-step storm spotting. That's what you came here to learn, right? So let's learn about some of the ingredients that go into severe weather. Because at any given time, there's about 1,000 thunderstorms going on someplace around the planet. Only less than 1% of those actually end up becoming severe. There's 4 ingredients that are needed to produce severe thunderstorms: moisture, instability, a source of lift, and shear, MISS.
The first ingredient is moisture. Moisture coming up from the Gulf comes into our area on the jet stream, brings all the moisture. If we don't get the moisture, we don't have clouds. If we don't have clouds, we don't get the severe weather. But the water vapor, the moisture comes up, condenses in the clouds. That acts as the fuel for storms and severe weather. When we measure moisture, we don't look at the humidity because that can vary all the time. What we look at for predicting storms is the dew point. Dew points of 60 to 65 degrees or above make it very good circumstances for a storm to occur.
Yes, severe weather can happen and has recently, sometimes happens when temperatures are below that and dew points are below that. So it's important to remember that severe weather can happen, but when you start getting into the higher dew point levels, the risk of it goes up. Instability is our next ingredient. Basically, an unstable atmosphere means that there's warm air near the surface and humid air near the surface, and cooler, drier air aloft. The warm, moist air wants to go up. It allows for the air not only to rise, but actually accelerate as it goes up. Updrafts in those areas can sometimes exceed 100 miles per hour in the strongest updrafts.
The next ingredient is lift. What causes air to lift? The difference between a cold front and a warm front. The cold air or the warm air will rise. The heating during the daylight hours. Elevated terrain, the low pressure systems, things like that cause the warm air to rise. When this warm, moist air rises, it starts to form into a storm.
So let's take a look at some example of some updrafts.
Okay, as you can see on this one, these are updrafts. Warm, moist air feeding in from the bottom, fueling these updrafts. Notice the sharp shape to the cauliflower type clouds. Our typical cumulus or towering cumulus, like are happening over here, starting to build into a possible thunderstorm.
So that next ingredient that we see inside of the severe storm, the severe storm ingredients, is wind shear. Wind shear is basically winds changing speed and direction at different levels in the atmosphere. The higher you go, there's less friction and they can move faster. This allows for more intense, longer-lived thunderstorms. The vast majority of significant severe weather comes from rotating storms or supercells.
Okay, we've looked at the step-by-step, or we're going into the step-by-step storm spotting now. We're going to learn about the different parts. We're going to learn to identify updrafts, downdrafts, how to assess storm strength and potential, determine storm motion and the safety of your location, and how to report that critical information back to your spotter group or the National Weather Service.
Updrafts and downdrafts. Updrafts are basically, that's the rising air. Warm, humid air fuels the storm. It's thick, puffy, billowy clouds that indicate the healthy updraft. Downdrafts are sinking air. This is the rain-cooled air that rushes out beneath the storm, frequently contain heavy rain, sometimes possibly hail, and it's that interaction between the updraft and the downdraft that is so crucial in determining thunderstorm strength, longevity, and severity.
The evolution of a thunderstorm. When we look at how a thunderstorm starts, the towering cumulus stage, like we showed in the earlier videos, it's just getting started. Mature thunderstorm, you have the updraft, hits the stratosphere around that 50,000 foot level, turns into a downdraft. The downdraft is cooled by the rain, possibly hail, coming down into that area. Once the storm matures, the updraft disappears and you have only downdraft. The storm is raining itself out, the dissipating stage.
This is what we know as the supercell schematic. And basically what you're looking at is, I think we like to joke about the fact that all storms look exactly like this. Well, that's not really the case. But what we'll look at here is the various portions of a storm in this example, and then we'll look at some real photos to see what we understand them better.
Okay, what we're looking at here, we have the updraft, the warm moist air feeding into the updraft. It hits the stratosphere, and if it's hitting fast enough, it actually shoots through before it starts coming back down into the downdraft. The downdraft is darker. This is where all of our rain is, all of our hail if it occurs, and that comes out in various directions. We'll talk about these other features of the storm and then further on down in the program.
So here's a few different photos that we can see of actual photos, actual visuals, because they don't always look like that nice, beautiful schematic.
We have the updraft again coming in, and notice the tornado portion is actually part of the updraft and the downdraft. Something we didn't mention before and we want to talk about continuously through this program is storm movement. The rainy area, the downdraft portion of the storm, leads the storm. So this will come through first, followed by the updraft. So when you're looking at something like this, it's moving from left to right.
So most thunderstorms really aren't textbook supercells. We're going to dig into some more examples.
Here we're looking at a cloud starting to form towering cumulus, the updraft portion of the storm, just getting started. Notice the flat updraft base. This is where the other things happen. The features of the updraft will occur at this level.
Here's another example. Could be the same storm slightly later. We have two towers here, two updraft towers. Again, you'll notice the strong, sharp edges on it, cauliflowery look to it as they billow up into the sky.
And here we have a mature storm looking at it actually from underneath. This is the inflow into the updraft. And on the far side, we can actually see the anvil up at that 50,000 foot level. You can't see a lot of definition, but it is very sharp. The clouds here in the inflow are very sharp, as is the edge of the anvil.
Now, if we were moving back another 20 miles or so, that big storm might start to look like this. Beautiful example here. Again, we see very sharp edges within the bottom portions of the storm here. That tells us there's a lot of strength, a lot of energy going on inside of that. Builds up there, spreads out at the top when it hits the tropopause, the stratosphere, and spreads out to form that anvil.
And you'll notice some of the others, there's other towering cumulus starting to build up out in the farther reaches behind it.
Mm-hmm.
Here we're looking at the anvil from almost directly below. You can see the inflow into the updraft. Notice the sharpness of all the clouds. You can even see a little bit of a manus hanging underneath the top of the anvil.
Now, if you compare those previous slides with this one, what you'll notice is the fact that these slides are a little bit different. It's possible that that same storm has kind of rained out a bit here. The edges here at the top are more feathery, they're lighter, frothier. Don't have the sharp edges that we had before.
I can point out the downdraft right here where all the rain is. It's probably cutting off the upflow to the storm. It looks like we have a question, Dave.
Question is, do you typically see hail from storms that push higher into the atmosphere and have more chance for the precipitation to freeze, or are there more factors?
There are more factors, but the best way to look at it when we start is that hail starts typically around, you'll get small hail that might form as low as 24,000 foot tops, but as the tops of the storm get higher and higher, the chance of hail being larger goes up. Also, that feeding into that, though, is the fact that if the updraft, if the hail as it's coming down gets pulled back in to the updraft zone again, it can make another trip up, get coated with more water, and end up being larger. Large hail tends to not be very smooth at all.
No.
And what you're typically, it looks more like a whole bunch of little pieces of hail all stuck together.
And we'll have pictures of those later on in the program.
And guess what? That's basically what it is, a whole bunch of little
Yeah.
pieces stuck together.
Now looking at another example here, is this strong or weak? Actually, you have two systems. A weaker system that's all feathery and raining itself out. You can see all the rain coming down. With a system back here that looks pretty sharp yet. Is either mature or maybe still building yet.
So those visual cues that you're looking for to understand storm strength. A strong storm has sharp, crisp cloud edges. Visible upward motion. You can typically watch those things build in real time. Well-defined updraft and downdraft regions. They're not very confused. Visible rotation can sometimes happen. And mammatus clouds form underneath that anvil.
Now the weaker portions of the storms, when a storm is weakening and dying, You'll see fuzzy cloud edges. It's weakening. Weak upward motion. Ill-defined storm structure. You won't see that sharp cauliflower shape anymore. Little or no visible rotation. But Dave, could you go back to that last slide for a second?
Yeah.
The thing to remember here is storms can cycle. Just because this one is dying, it could rebuild in a half an hour. They will go through a cycle until it runs out of fuel.
Good point. So let's take a look at another video here, time lapse in this case, so that you can understand what that updraft looks like.
Okay, what we're looking at here is your towering cumulus, your updraft. These gray clouds that are moving through, this is actually inflow, or this is your warm, moist air feeding into the bottom of the updraft. Notice how it's starting to explode on top. It's reached that stratospheric level where it's flattening out, spreading out. And all this warm, moist air is feeding into the bottom as this storm continues to grow. And here we're looking at it again underneath the anvil, as you can see this spreading out. Now this is time-lapsed, of course, but you can see the warm, moist air going into the inflow as this continues to roll out. Stepping back a little bit, you can see the mammatus clouds hanging underneath the top of the anvil.
So here's some comparisons here, some photos that give us some good examples of the differences between those updrafts and downdraft sections. The updraft on the left-hand side is rain-free, nice relatively flat base on it. The right-hand side is the downdraft. Is it strong or weak?
This would be a strong storm, Dave. A thing to remember, we'll talk about storm motion. With the rain leading the storm, the updraft following it, this storm is moving from left to right.
What do you think about this one? Strong or weak?
Well, Dave, this one looks a little weak. You don't see any sharpness in the clouds. You can see the updraft base yet, but you really don't see any inflow. So this appears to be raining itself out and dissipating.
How about this one?
Wow, this one looks nasty, Dave. You can see the sharp inflow. You're so far underneath the storm, you're not seeing all the cauliflower features, but this is a strong inflow areas. This is all really sharp. Notice the dark blue colors inside the storm. That's the hail. It looks blue because as the sunlight reflects off the ice crystals, blue light comes out. So whenever you see blue light in the middle of a storm, it's not a UFO, it's probably hail.
So let's take a look at another video here, approaching a storm and then looking at a funnel.
It's going to be really weird to see a tornado today with snow still on the ground.
Okay.
We just passed Jacksonville, Illinois. We are approaching a severe warned storm. You can see the rain-free base on the left side of the frame there. There's even a little dippy-doo lowering there in the clear air. That's where our main area of interest is right now. Okay, looks like we might have a funnel cloud here. Looks like we have a pretty distinct funnel cloud now. Storm is still severe warned. I'm going to try to hop on Spotter Network here and try to report this thing to the Weather Service.
Here's another video. Again, this one going to be looking at storm structure, but we'll do this in time lapse.
Notice the rotating storm structure here as it feeds into the updraft. This is all the warm, moist air getting sucked into the updraft. And notice this is time lapse. The movement is very fast compared to what it would be in real life.
And one more video to take a look at here.
Here we're looking at a rotating wall cloud. You can see how everything is spinning, the rotation of the updraft. You can see some of that blue light back in there. Here's another look at it. This is an actual real time right here. So you don't see as much movement as you did in the time lapse.
Good reason that you need to be patient when you're looking at this.
That's right. You stop and see something that looks like a feature you need to be reporting. You sit and watch it, see what it does. Is it lowering the rotation underneath? The amount of inflow are all important factors, and if you need to report these to the Weather Service or to our spotter group.
And we have one more video here, again structure with a rotating base and inflow.
So it might rotate towards us. Watch that lowered area for spin-ups.
Right down there, brilliant.
To the right of the road, above the hill.
Oh, right above the hill, that's what I was looking at.
Also to the left of the road, there's a bit of a lowering. For that one, there. Just look at it.
Our next updraft feature that we want to take a look at is the wall cloud. The wall cloud develops under the updraft base, which indicates if there's rotation. Actually, it does indicate that there's rotation. It's the area of strongest rotation within the cell. It's typically a first sign towards tornado genesis, if it's going to happen at all. Usually it's tilted downwards towards the rainfall and the downdraft portion of the storm. Looks like we've got a question.
Actually, I have two questions here. The first one is, what causes the clouds to turn into a shelf cloud? And the second question is dippity-doo an official storm spotter term?
Well, the shelf cloud portion of that question we're going to get to when we start talking about the downdraft portion of the storm. It is a downdraft feature. Wall cloud, which we're talking about now, is an updraft feature, which is why it's so important to understand where you are in relationship to the storm. And the dippity-doo thing? Yeah, maybe not, but you know.
That's a new one to me, Dave. So here we're looking at an actual wall cloud. This is your updraft base. Yeah, your updraft, downdraft, your base right here, your inflow, updraft base, and this is your wall cloud underneath. Notice how it's not really sharp, but it would be pointing towards the rain. Now we talk about storm motion again. Remember, the rain comes first. So this, followed by the updraft, is moving from left to right. It's important to know how storms move so that you can be properly positioned, and also so you know what features of the storm you're actually looking at.
So while the wall cloud in the previous slide was very spectacular, very easy to spot, most of them are a little more nondescript. Here we have a healthy storm that's evident by the structure of the clouds in the downdraft section. But note that the rain-free updraft region on the right and the dark downdraft on the left. Underneath the updraft base, we can see a wall cloud. Well, we have to watch this storm to see if it rotates visibly or not, whether that increases or if the wall cloud lowers more towards the surface. At the moment, it looks pretty benign.
Yeah.
Now again, storm motion. In this case, our updraft is on the right and the downdraft is on the left. So our storm motion in this case would be from right to left.
But again, look at the sharpness of the clouds. This storm is still maturing. It has not, there's good things yet to come out of this if you're looking for severe weather possibilities.
Certainly one to keep an eye on.
Yes. Now looking at this wall cloud here, we're actually kind of strange because we're seeing some blue sky up above, but we have the updraft going up with the downdraft over here. Little wall cloud right there pointing towards the downdraft. Again, this storm motion is from left to right.
Another beautiful wall cloud here. I think this is a very photogenic one. And again, what you're looking here is the downdraft section is on the far right in the background. We're under the updraft base, and we see the wall cloud that's descending below that updraft base, and again points down towards the intersection with the downdraft. Storm motion on this, probably going to be it's more or less left to right, but away from us as well.
In this particular storm here, again, we're underneath of it, so we can't get any distinction on the shapes of the clouds. But here we have the warm inflow going into the updraft, wall cloud underneath, with over in the far left there is going to be your downflow, or your downdraft section of the storm, with the rain in it. This storm is moving from right to left.
So questions, not all wall clouds are tornadic or even lead to tornadoes.
That's right.
So the question is my wall cloud, that's kind of taking ownership of it, is my wall cloud tornadic?
Did you win that on The Price is Right? Or?
Oh, that could be exciting.
Yeah.
We want to take a look for persistent rotation. Rotation can happen in waves, but watch the storm for a few minutes. Is the rotation speeding up? Is it slowing down? How fast is it going? How low is the wall cloud down to the ground? Descending wall clouds are a possible sign of developing tornadogenesis. How strong is the inflow into that storm? Increasing inflow into the storm is a sign of developing tornadogenesis. Are there any signs of a developing funnel cloud? Look for enhanced areas of rotation and lowering. It's like we have a question.
Jerry says from left to right, but what if you're on the other side of the storm?
If you're on the other side of the storm, you'd be looking at a different picture, and in that case, you would probably be, if it's left to right on the one side, on the opposite side, it's going to be right to left.
Just remember that the downdraft leads the updraft. The storm, if it's moving towards you or across where you're standing, the downdraft with the rain comes through first, followed by the downdraft.
Now, one of the items that was listed in here, how strong is the inflow into the storm? You can notice that from the fractus clouds or scud clouds that are located at the bottom of the storm being pulled into the updraft. That's one of the ways. The other one is just the wind that's being pulled in. If you're looking at the updraft portion of the storm and the wind is at your back, that tells you that's the updraft. If it's a strong wind, that's going to be a stronger updraft.
Okay, tips for identifying rotation. In general, if there's rotation in a storm, it will be obvious. You'll see the cloud movement in a circular pattern. Watch the storm for a few minutes. Make sure you're looking at the updraft portion and not the downdraft. And watch for rotation along a vertical axis this way, not a horizontal one. That'll bring us to our shelf clouds, which we'll talk about in a few minutes. If you're not sure about the storm, rotation is either weak or non-existent. but continue to watch it and see what happens.
So let's take a look at some videos of wall clouds.
Okay, what we have here is just slow moving. This is real time. This is our warm, moist air feeding into, to the wall cloud. You can see it's hanging down from the updraft base. Very little movement that's detectable, but you can see a little bit here. So very little movement in this, but continue watching. You want to watch if the wall cloud, if it's dropping or rising. Now here you can start to see a little rotation. Obviously something you want to be reporting. The problem you may encounter here is if this wall cloud is behind the tree line, you can't see what's happening.
Looks like we have a question.
Yeah, there was one that asked, what is the definition of tornado genesis?
Tornado genesis is just the process of starting and building a tornado. And we'll actually dig into that here very shortly. Let's look at another video here. This one, interestingly enough, is not time-lapse. It's in real time. And the rotation will tell you it's a very strong storm.
And this was southern Minnesota, June 17th, 2010. Like Dave said, this is real time. This is your wall cloud. Just watch it. This thing is coming up very fast, forms very fast. Here you can start seeing the lowering. We're watching for the lowering. Also notice the inflow here, how quick the inflow is moving in real time. Continuing to build and lower. And boom, we have a tornado. Probably less than 30 seconds from beginning. And it's really quite one of the money shots for tornado formation. This has been excellent. Very seldom you get to see one in Minnesota that is that clear.
And our last feature of the updraft is tornadoes itself. So first of all, Jerry, what is a tornado?
A tornado is actually a rotating column of air attached to the wall cloud or the updraft base and the ground. It has to connect to both in order to be qualified as a tornado.
It's typically preceded by a wall cloud and usually a funnel cloud. Yeah. The funnel cloud may or may not be visible even as tornadic circulation is on the ground already. It'll often initially be evident as rotation or debris on the ground. That's when we know that it's actually touched ground.
And we probably have as many of those as we do solid tornadoes from top to bottom.
Mm-hmm. So is this one a funnel or a tornado?
Well, Dave, we're not seeing any rotation underneath or any debris field. So this we'd have to classify as just a funnel.
We're looking at a series of the same storm here. What about now? Funnel or tornado?
This is zoomed out, but still, we really can't tell for sure if there's any debris there. So if there's no debris, we can't call it a tornado.
It's got great storm structure, though, when you're panned out like this.
Oh, yes, you can see the inflow coming from all the way back here. If you saw the movement in that, you would realize how strong this rotating wall cloud is.
How about now?
Now we have a debris field underneath. They're not quite connecting, but about 90%. But once you have debris on the ground, a funnel coming from the wall cloud, we can call it a tornado. And here in the final slide in this series, you can definitely see we have a full-strength tornado on the ground.
In this case, the funnel itself condensation funnel is touching the ground.
Right.
So what about this? Are we looking at a funnel up there at the top, or are we looking at a tornado?
Well, that's a good question. It could be deceiving because you're looking at this funnel in the updraft base. You know, again, rain-free, but you notice we have a debris field down here. If we continued to watch this, we might see the connection of the vapor cloud form. But this would be called a tornado.
And here's another great one. Don't you love this game? Funnel or tornado, Jerry?
Okay, we definitely have one farther here over on the side, and this is a huge wall cloud with 1, 2 more tornadoes, or possibly tornadoes. We can't quite tell for sure from this shot, but possibly 3 coming out of this same wall cloud. So we have to remember, don't get watching one thing too long. You have to be watching all around, you know, your head on a swivel. You don't want to be watching one tornado and get smacked from the side by another one.
Looks like we've got a question.
Yeah, from the chat box, when a tornado is creating itself, what would be the average temperature drop we would feel?
That's a wonderful question. I'm not sure that I would even know that.
Well,
typically we're in the warm section of the storm.
Yeah, the temperature drop is going to come from the outflow portion, the downdraft of the storm, where the tornado is actually in the updraft. So if the storm was moving towards you, you would have warm, moist air. Then you'd get hit by the downdraft, which would cool you off. And then as that moved through, you'd probably move into a warmer section of the storm again, into the upflow, if you wanted to be that close to it.
I have another question. If a debris field was obscured by rain or a tree line, as spotters, how would we report it?
We've got some examples of that coming up too.
We do. You report only what you actually see.
And I think a perfect example of that one is coming up, but because sometimes you can't, because of the trees, because of a hill, obstructions, you may not be able to see the actual what's going on the ground. Report what you see.
And again, we've got a split slide coming up that will show us about that.
So, funnel or tornado?
Well, this is a good one. It's a still picture, but even if we had live motion on this, you would not see any rotation in any of this. This is SCUD, or scary looking clouds, as people often like to post on Facebook. You won't see any movement from this, except maybe if it's moving up into the updraft or just slightly back and forth. You won't see any rotation.
How about this one? Funnel, tornado, nothing? What is it?
Well, I think we got a funnel, and we've got a long wall cloud coming around here, but all we've got is a funnel so far. There's nothing on the ground to indicate debris. So you call what you see. That's a funnel.
Again, report only what you see, but keep in mind that other spotters might have a better view.
So it's important to call in and tell us, hey, I see something that looks like it might be a funnel, because a person just down the road might have a better view of it. And even though it might be a second or two later, he actually can report the tornado there. It's actually occurring from his vantage point.
So let's look at some videos here. This time a tornado and an inflow band. Wow.
Look how fast that inflow is surging in. New wall cloud back there. There might be something in there.
Oh yeah.
Whoa, there might be something in there.
Very important to keep your head on a swivel. If you're looking at a large storm system like that, keep looking around because there can be other portions of the storm very close to you. Other cells within that storm system that might be a little more advanced.
Normally, you'd want to keep a couple miles away from the actual inflow portion of the storm.
So another one here, tornado. Let's take a look at this video.
Now what we're looking at here is the inflow. Here's a very weak tornado coming down. Notice how it didn't quite connect, but here we have the tornado, the debris on the ground. And you really don't see it here for a while, but wait until it crosses over the road. And there it is again. Once it hits dry dirt, picks everything up. Not a huge tornado, probably an F0, maybe an F1 at the most, but more than enough to do significant damage to buildings or property. Now something like this you could report because you're actually seeing debris even though it was behind the trees. Here you're looking at the funnel up above, not quite connecting, but we have the debris field.
And the tornado itself actually is that column of air.
Yes.
Whether or not it's got a condensation funnel with it or not, that's what you're actually looking at. And now we've got another video, multiple vortex tornado in this case.
Here comes again.
Oh my goodness.
Oh my God.
There's like, they're dancing around each other.
So cool. Keep
Oh, it's violent.
Look, and now it's a big wedge. You just tell me if we need to run. Okay? Take it down, Molly. I am. What was that little town on the corner there, Brett?
Leaf Valley.
Okay, all right.
Leaf Valley Township.
Okay.
Oh my gosh. Oh my gosh, there are two.
Yep. There's a bunch of them right here.
Just keep taking pictures.
I am.
It's going to cross in front of us there in the road. Or...
Yeah, it's going to cross the road, but it is a multiple vortex tornado right here. This rapid rotating meso.
This is Peggy Willenberg of Twister Sisters. We have a multi-vortex tornado.
That's some very strong rotation on that one.
Yes,
and you'll notice when that portion of the wall cloud is rotating as much as it is in that case, that there can be deception as far as where those various tornadoes look like, those multiple vortexes are. And there's a great example from that in this video.
Okay, what we're looking at here is the formation of this tornado. And you can tell a relationship according to these posts and poles in the background. But this tornado is rotating around the wall cloud, so you see it moving from left to right. It's actually dissipating a little bit, kind of roping out. But as this whole wall cloud rotates, all of a sudden the tornado starts to move back in the other direction. You can see it quite plainly there as it moves back from right to left. So yeah, you have to be very aware of what's happening all around you. Looks like we have a question, Dave.
Question is, I've always heard people say that you can't outrun a storm. Is that true?
Storms vary quite a bit, but the reason that you don't want to try to outrun a storm is the fact that, number one, they can be moving very, very quickly. Number two, they can behave erratically. And number three, you get into situations where you're in decreased visibility, or if you're in the updraft portion where a tornado would be located, the rain's probably already come through and the road might be deteriorated to the point where you're really not going to be wanting to try to outrun that thing.
Yeah. Once you're in the storm, it's too late. You're not going to be outrunning it anymore. You just have to seek shelter or stay in your vehicle, try and stay safe. Or if you're working with a spotter group like us, we will tell you if it's safe to move in another direction or to stay where you're at.
We've got another video. This one is a high precipitation because that's another risk that comes when you're spotting tornadoes.
This is what happened in 2010 again to some of our local tornadoes. The rain actually wraps around the wall cloud, comes in and obscures the tornado. You can see the inflow band back here feeding into the storm. Large inflow with actually pretty decent movement. So you know this thing is active yet. But if you didn't know, right at this moment, you wouldn't be able to tell if there was a tornado inside of that. Now here, as the rain dissipates, you can start to see, they're zooming in on it, just so you can see the shadows of the tornado back inside the wall cloud, hiding within the rainfall.
I've had that one before where I've been stuck in the rain within a half mile or so of the tornado. Not a fun place to be.
No, and that's brings up another thing is communications, because I know the very first years I was spotting, I was using a cell phone. And I couldn't hear what was going on, what was happening on the amateur radio bands. The following year, I got my ticket and became an amateur radio operator, so I knew what was happening.
It makes a difference. So let's move on. That's our updraft features. Let's start talking about downdraft. It looks like we have another question.
Yes.
On your cell phone versus amateur radio, can you listen to amateur radio being a non-ham?
Yes, you can. You can listen on your amateur radio without a license. We encourage you to get a license. It's not difficult. But you can listen effectively, with what's happening. You just can't participate in the conversation.
One of the other things that's important to note about that is that Minnesota's laws prohibiting use of radios that can receive police bands. That means scanners are not legal to be used in vehicles.
Unless you're an amateur radio operator.
However, if you're an amateur radio operator, you can.
Now, Bob, maybe I need some clarification. Did you mention cell phones as part of that?
Well, that was in reference to your cell phone item.
Because I'm not sure, because there are some phone programs that will tap into, the amateur radio communications.
That's true.
And you can listen via phone, but something I'm really not familiar with, because I don't need to.
Well, we've talked about our updraft features. Let's move on to the other part of the storm, the downdraft.
And remember, we're looking at a storm, that warm, moist air going up. Everything that goes up has to come down. The downdraft feature is the dark portion, contains the rain, hail, strong winds coming down. The updraft-downdraft balance determines the strength and longevity of the storm. If one is taking over from the other, if the updraft is stronger, the storm is still building. Then you kind of have the mature equal stage like we talked about earlier. And finally, if it's all downdraft.
There's your updraft.
And the downdraft. Well, let's talk about storm motion again, Dave.
Storm motion in this case again, from left to right. This is a downdraft. It's actually what we're watching happen here in a radar loop is we're watching a storm rain itself out. Big downdraft, hits the ground, pushes out, and that line that you see around the storm is the outflow boundary.
Okay. Here we're looking at part of the downdraft feature. It's important to notice right here, one of the downdraft features is the outflow of the wind, which stirs up dust and pushes dust ahead of it. So if you know you're looking at the downdraft portion of the storm, this is dust moving out ahead of it. Here again, we're looking at the downdraft portion of the storm. We can see the rain back here, the downdraft portion of the storm, winds rushing out, high-speed winds, pushing the dust ahead of it. Notice some of the clouds hanging up here, some of the scary-looking things that's not a tornado. You have to be aware of what's happening, what you're looking at. This is the outflow from the downdraft and blowing dust.
In this case, what might not be clear from the photo is where we are in relation to the storm. We're in front of the storm. You're seeing the storm as it's approaching you. So that's the storm front or the gust front that's coming out front that's picking up that dirt. Not a tornado. You might be confused because of the rain-free base here, but this is actually under the front of the storm.
And here's another gust front blowing out. Here we have the rain downdraft on the far side with the dust blowing out in front of it. So storm motion on this, just looking at this picture, is going to be from left to right.
So talking about shelf clouds.
Yes.
Shelf clouds occur, they are a downdraft feature. Important to note. If you know where your updraft is and you know where your downdraft is, you can help to identify features. Shelf cloud is located at the leading edge or towards the leading edge of the storm. It's where you find the gust front. Strong winds often follow immediately after the shelf cloud. It's most common when you're talking about squall lines or linear storm systems. There's no vertical rotation. That's something that's typically found in the updraft portion. Yeah. But you may see exhibit some rotation along a horizontal axis.
Well, something we want to look at on this particular shelf cloud, and what you're looking at is the storm actually moving towards you. You have the downdraft coming out of the downdraft of the storm, the winds coming out, running into the warm, moist air in front. The warm, moist air rises over the top, and that's what makes the layers on the shelf cloud. It may also initiate the rotation along the front of the shelf cloud. You've got cold air coming out from underneath with the warm air sliding up the top, creating rotation in the clouds.
Mm-hmm. It's not required that it be there, but it can happen. So don't be scared of it. Another shelf cloud.
Yeah, another shelf cloud. Again, when you look at these, if you're in front of it like this one, it's going to stretch from horizon to horizon. We're going to show that in an upcoming video. Notice some of the scud hanging underneath here. Nothing to worry about, but you may see some rotation, which probably come in another slide.
One of the things you'll note about shelf clouds is their size. They tend to be huge, stretching oftentimes from horizon to horizon. You're not going to find a wall cloud that reaches from horizon to horizon. Want to describe this one a little bit?
Well, again, you've got the cold downdraft coming out in front, running into the warm air, and that's creating these layers as it feeds back up into the storm. Here we're looking at one coming the opposite direction. We're actually, I don't know if they're up in an airplane or how they're looking at this one, Dave, but you're quite elevated, but you're actually looking in to this roll cloud. They're calling it a roll cloud because at this point they're obviously seeing rotation from the cold downdraft coming out, the warm updraft feeding in.
Let's take a look at a video of a shelf cloud. Look at the incredible size of that.
Yeah, and that's the thing about a shelf cloud or a roll cloud. They just stretch for miles.
Looks like we have a question.
Question from the group here. Are shelf clouds a telltale there will be severe storms?
Not necessarily. Shelf clouds can form in front of quite a number of storms. Again, they are a downdraft feature, telling you that there's moisture coming back behind and pushing that cold air is pushing out in front. They don't necessarily indicate that they're going to be severe, but you're typically looking at a gust front. The wind is going to be picking up at some point. Whether it turns out to be severe is really going to depend on what happens a little further back in the storm. Let's look at another video. This one in time lapse. Helps us to understand the shelf cloud a little bit more.
Okay, we're looking at the shelf cloud coming along, again, extending from horizon to horizon. Notice all the scud or the scary looking clouds hanging underneath. It is something to watch, something to keep an eye on, because as we learn later about our QLCS storms, something can develop out of it. It's very unusual, but it can happen. But you're not seeing any rotation in any of this. Just all moving right along. You'll get that gust front. You'll have wind at your back for a while. You're looking at the storm, the wind is at your back, and all of a sudden it'll turn. You'll get slammed right in the face by the gust front out of the downdraft.
So looking at this one then, another game, shelf cloud or wall cloud?
Well, that's a good question, Dave. I got to look at this for a second myself. This looks like a downdraft feature. You can see the dust blowing out in front. So this is a shelf cloud.
So, differences between shelf clouds and wall clouds. First of all, again, remember where you are in relation to the storm. If you are in the updraft zone, you'd be probably looking at wall clouds. They're an updraft feature. They rotate around a vertical axis. They're attached to the inflow base. They're associated with tornadoes, if they happen. And they're typically a feature of supercell thunderstorms, though they can happen with other types as well.
But then we look at the shelf clouds. A shelf cloud, we're back to, it's a feature of the downdraft or the outflow portion of the storm. You're going to see horizontal rotation if there is any at all. It moves along the outflow. It's often followed by damaging wind gusts. You can have very strong straight line winds or the downdrafts we talk about, and these are typically a feature of a squall line.
So, shelf cloud or wall cloud?
Actually, we're looking at both here. When a supercell storm is strong enough, it pulls the shelf cloud back around into the updraft. Next click, Dave. There we go. There's actually a wall cloud forming back here in the updraft. We'll show you in a video coming up of what this looks like on radar.
So, shelf cloud or wall cloud?
Again, we're looking at almost an identical storm here. We have a long shelf cloud, but it's being pulled back in a curve into the updraft portion of the storm. Again, must be a wall cloud back here, possibly a tornado even.
There's your downdraft.
There's the downdraft.
There's that updraft.
Pointing back to the updraft, Dave.
Here's a fun one. Shelf cloud or wall cloud?
Again, I think we're looking at probably both here. You're looking at a nice wall cloud with good inflow, but this layer back here is actually coming back from the front of the storm. You can see the downdraft up in front, the rain. So we're looking at storm motion here from right to left. Now here's the radar we talked about, Dave. You want to explain the hook echoes?
Radar imagery in two different supercells here. Oftentimes people talk about a hook echo, and this is a great example of that. They don't necessarily are visible this far away from the radar site. They can be hard to see, but this happens to be a little bit easier. And what you're seeing here, the radar picks up the intense precipitation. That's what you're seeing.
And let me move back behind you here.
And you'll notice in this situation that intense precipitation then is getting pulled around a rotating storm and forms that little hook. Right at the tip of that is where we're actually seeing a tornado in this case.
And that demonstrates the power of the updraft in these supercell storms. We don't see it quite so much in Minnesota, but yeah, these classic hook echoes, just like is formed in this motion here.
Let that play one more time through here as we see again that storm being pulled around, see that formation of that hook. Eventually it'll cut itself off, but that's what's going on there.
And noticing the speed of the storms here. You notice how slow this moves. I think we're supposed to talk about that later. But these other storms are zipping by while this supercell just kind of hangs.
Let's talk about squall lines.
Finally. Squall lines are groups of storms organized in a line. They can be hundreds of miles long, but are typically only 10 to 20 miles wide. They pose the great risk of high-speed damaging winds. Part of this is derechos, which are intense squall lines that can produce damaging winds over 80 to 90 miles an hour. Certain cases, tornadoes can be embedded in these squall lines. These are called quasi-linear convective systems. What I want to point out here is the bow echo right here. When you see this bulge, that is the portion of the strongest winds coming out doing the most damage. We had one just last summer move through eastern Iowa, did many thousands of acres in crop damage. We've had them in northern Minnesota. They actually are fairly common coming down this way, doing thousands of acres of damage in the woods and timber.
And it looks like we have a question.
Can tornadoes happen in snowstorms and blizzards?
That's a great question. Very unlikely. Let's put it that way. I wouldn't rule it out, but it's very unlikely.
Well, if you live in Minnesota, you can have tornado warnings one day and a snowstorm the next. But they usually don't happen together.
What you're missing when you're in a snowstorm is you're missing that warm, moist air that fuels the storm. Again, it's one of the key ingredients in a severe storm. So let's drill into those quasi-linear convective systems and talk about the QLCS tornadoes.
Okay, actually later, this is the moving section of the radar. After a while, we'll have a still we can talk about a little bit better. But it's commonly, if there's going to be a tornado in these systems, like we had in 2018, they're going to be weaker and shorter duration than supercell tornadoes. They're still very dangerous, but they're very difficult to spot because they can pop up anywhere along the line. But beware, when we looked at it before, how straight the line was, how this has all the curves and bumps and hooks in it.
QLCSs typically happen along very rapidly moving squall lines. If that's going to be happening, and what happens is you're pushing forward and some portions are a little faster, some portions are a little less. That difference in speed provides a touch of rotation. Again, extremely difficult to spot. Let's watch a video here in Owatonna of a QLCS tornado.
Now this right here is the squall line moving through, and all of a sudden you'll start to see movement. You notice it's not as smooth as it was. You're starting to get some of these kinks and bulges in the squall line. We need to look at this portion right here behind the church steeple, and you're only going to see it for about a second because unfortunately the people had to leave the area. But look at the structure there a little bit too. It's developing all of a sudden on the leading edge.
You can start to see rotation there. As they play through it in time lapse, you'll notice it happens very quickly.
Yeah, right up in here. And yeah, it's too bad they couldn't have kept filming for about another 10 seconds. They would have had a good shot of that tornado.
Well, they decided to be safe, and
Well,
that's a good thing.
And that's what we always talk about, is spotter safety is important.
So, here's another great example from that same day. Are we looking here at a quasi-linear convective storm?
Well, we really don't know. We are seeing a little bit. You know, this is your shelf cloud. And quite frankly, we weren't looking for anything. We were experiencing the strong winds. This passed through an area right where I was spotting at. You see a little bit of scud underneath, but give it time. All of a sudden, things start to happen. This did develop a bit of structure to it. You had some rotation. It did have possibly hit Ellendale down in southwestern Steele County. It did not get investigated as a tornado, although we suspect it was, but it was not verified.
There was a lot of things that day, and it was difficult to capture them all.
And frankly, we just weren't expecting tornadoes coming out of a squall line at that point. Now we know better.
Quasi-linears, again, we talk about rapidly moving squall lines. And in that situation, those rapidly moving ones, that's when the tornadoes, if they're going to form, are probably going to be on the front edge of the storm instead.
Yeah.
But again, they tend to be short-lived and usually not as much damage. Let's look at another video here of a quasi-linear tornado.
Now they're driving along underneath the shelf. This is a shelf cloud out in front. But watch the tornado starting to form up there in the middle. I think they will change the viewpoint of the camera right here in a few seconds. But you can definitely see something starting to bulge, and there you have your tornado. There was a little bit of a segment gap right in there. But again, these are usually weaker. They don't last as long as a supercell type tornado. Notice there it's disappearing already.
So let's look at some storm spotter safety, because frankly, that's our most important goal, is taking care of our spotters. Your safety is the utmost importance. If you're not safe, you can't provide that information to help keep other people safe. Situational awareness is the key. So what is the storm motion? Where's the updraft? Where's the downdraft? What's that storm motion, and are you safe in your location? Are you at a safe distance? Are there other storms that are also located in the area? Are you safe from lightning? Lightning kills more people than tornadoes does.
And we don't talk a lot about lightning. It's important to stay in your vehicle with the windows up. Don't be standing outside watching the storm as it rolls in. The lightning can strike up to 10 miles out in front of a supercell.
How about hail? How about flooding? Do you have an escape route? Ideally, you should have multiple escape routes. And pay attention to what's around you. Is there a place of shelter? Remember, visibility can often be very degraded around storms.
Storm motion. When we look at storms, they generally move from west to east. It's just the way they are here in the Midwest. Supercells may exhibit deviant motion. We'll show that in a moment on some video coming up. They tend to move slower and to the right of other storms. So we have multiple ways of determining storm motion. We have the radar, which everyone should be able to have some type of radar in their vehicle or on their mobile phones. Also, you get the warning text from the National Weather Service. It'll tell you storm is moving east at 7 to 10 miles an hour. You got that. And then you have the visual cues. You're actually out there watching. Okay, this is the updraft, the downdraft portion of the storm. You know what direction it's moving.
And it looks like we have another question.
The person asked, not sure if it'll be covered in this training, But could you explain the millibar? What do they need to look for or know to look for on radar? The higher, the better we see precipitation, or the lower?
Millibars is one of the ways of measuring atmospheric pressure. It's the international one. The one we use in the U.S. is in inches of mercury.
Yeah.
What you're looking for is higher pressure in either of those two systems, either millibars or in inches. Higher pressure tends to be fair weather. Lower pressure tends to be stormy weather. It's the low pressure area which is where you're going to see storms forming. Low pressure also happens along frontal boundaries. That's a frontal boundary. There's going to be a change in wind direction, might be a precipitation change, might be a noticeable temperature change, not always, but there will be a change in wind direction, and that's the low pressure area as well.
And as far as watching the millibars as a storm moves in, it will tell you what's maybe going to happen. You know, if there's a storm coming. But as far as watching for tornadoes, millibar is not a good indicator. Mm-hmm. Yes, Tom.
I have another question. When we see a radar picture on TV, is that live in real time, or does it take some time to generate that image? And if so, how long?
Well, it kind of depends a little bit on what you're looking at, but most of the time it's safe to say that you're delayed some portion of that. Depending on the type of radar that's being used and where that source is coming from. We use a product called GR Level 3 predominantly. There's been some additional processing that's taken place. They're looking at multiple levels in the storm. They're looking at more information. And historically, that was up to about a 6-minute delay on GR Level 3 information.
And it's important what weather feature you're looking at. Something I stumbled across a few years ago, if you're looking at composite radar to get the beautiful picture, that can be delayed up to 10 minutes versus getting a one-slope shot.
Mm-hmm. One of the things the National Weather Service added recently, within the last few years I should say, is a different method of scanning the storm. They used to always just scan it in layers, one rotation, and then they tipped it up, go another rotation, tip it up further, go another rotation. Now, as storms are active, what they'll do is they'll take a few slices, come back and shoot the bottom, then go higher and finish out, and then come back and shoot the bottom again. And that gives us more timely information, but again, you're probably at least looking at a 2-minute delay.
Yeah, so it's going to depend on storm speed. If you're watching a supercell, it's not quite so critical, but like these squall lines we had come through in 2018, they come through so fast, the radar could be showing it miles away from you when it's actually on top of you.
Mm-hmm. Speaking of radars, and speaking of that day.
Yes. This was September 28, or no, this was our June of 2010 storms. We're talking about deviant motion. That's how the storms are generally moving to the northeast. But these cells right here, all of a sudden they start moving back to the northwest a little bit, right at the end of the cycle of this movement. Here you can see this one actually moving north. This storm is from Moore, Oklahoma. Same thing we looked at a little bit before. But again, noticing how the updraft in the supercell doesn't actually move that much compared to the storms that come flying by, to the right. The deviant motion of supercell storms.
So sometimes you can find the information within warning text. A tornado, in this case, they talk about is moving east at 35 miles per hour. The warning box, if you can happen to have a visual, also shows that. That polygon is pointing, it's narrowest on the left, and widest, which is the uncertainty, on the right. So that motion, again, is from left to right on that image. But if you're in the field, one of your best indicators of storm motion is to pay attention to the storm.
Again, we have our updraft portion of the storm, the updraft, the downdraft over here on this side. Storm motion is from left to right. So it's important to know where we're at in the storm. So I always stress this over and over again, what part of the storm you're looking at. It's important to know so we don't confuse scary looking clouds with the ones that really count.
Let's have some fun trying to put some people in place here.
Okay, here we have storm spotters looking at this storm. This is on the radar. We have spotter A. He's looking right into the best part of the storm. Let me move over a little closer to you. Very dangerous place to be. He's got a beautiful view. He'll get great photographs of the storm that he can sell if he lives. Spotter B is in an excellent spot. He can see where the tornado is at. He's going to be safe. Storm motion is moving to the northeast. Now we go down and look at spotter C. It's a very safe position, but probably all he's going to see is rain. Same thing with spotter D, back on the back side of the storm. He's out of the storm now, and he's looking at nothing but rain.
The other one I would note on number C there, as he's there, is pay attention to the other storms that are behind him. There may be more that are coming down the line.
That's right. Keeping your head on a swivel. We try and talk about it all the time, although out in the field, it's easier said than done.
Yes. So what about positioning for squall lines?
Here's our picture right here of our squall line from 2018. Nice slow picture. You know, it's a still picture. Spotter B right up here by Faribault. This is a storm that moved through Waterville, Morristown, and into Faribault and created tremendous amounts of tornadic damage. Right here where this bulge is, we know now that this is not a good place to be. There's, very close to the tornado. Spotter A, they're going to get hit by heavy rain. Spotter C down here, it looks to be relatively safe. Spotter D is back behind the storm. All of these were experiencing strong outflow winds from the downdraft. And even we're right here by Owatonna, we had tornadic activity came out of this. Again, down here by Ellendale in southwestern Steele County, something down here actually developed possibly tornadic. So you're really looking at radar, you can't always tell. B obviously was in a bad spot. C and A, you just don't know. It's very dangerous spotting in squall lines.
There really are no good safe locations when spotting on a squall line. All of the locations are going to be impacted by high winds and probably by heavy hail or heavy rain. So I guess the one thing that I would want to note out of that is make sure that you've got shelter nearby. And we saw some of the video from that day's events where they took shelter underneath an overpass. Not a great place, but you know what? When you can't drive through the pouring rain, it's about the best you had. There's some other mobile spotting concerns.
Here's another one. Big city spotting or spotting in traffic. This can happen out in the country in tornado-prone areas. You get all the tourists out, the storm spotters, you get into traffic and you can't move. This happens to be St. Cloud with a wall cloud moving through it. So driving can be more dangerous than a storm. That's why we really recommend that there's two people in the car, one to drive, one to spot. Always have an escape route when you're out spotting. Keep your engine running. The one thing you don't want to do is go out to a spotter point, turn your engine off, turn the radio and everything on so you're listening to the amateur radio, whatever's happening, and your battery goes dead as the storm moves in. So keep your motor running, your doors unlocked. Never drive around barricades. We'll hit on that in a moment, Dave.
Mm-hmm. There's also visibility concerns. Heavy rain, blowing dust, they can conceal the very updraft features that you're trying to find. Remember, it's important to maintain a safe 1 to 3 miles away from a standard updraft. Spotting at night, totally different set of problems, and we'll look at that in a minute too.
Yeah. And again, visibility concerns from the blowing dust and rain. This is a little ways off, but as these fronts move through, you just can't see what's happening. So stay, 1 to 3 miles away from the updraft in a supercell storm. And then again, we're going to talk about night spotting. It's very, very dangerous.
Back to flash flooding. You'll notice this was taken after the storm. We've got road barriers up, so it's been some time since the storm actually occurred. What we want to point out here is that that moving water, that flowing water, can actually undercut the road itself. First place, you don't know how deep it is just looking at the water. That's one problem because, 5, 6, 7 inches can actually, of rapidly moving water can take a vehicle off the road. The second thing to note, though, in that right-hand photo, is the fact that if the rapidly moving water can undercut the asphalt or concrete, it can take that underlayment right out.
And if there's standing water, you don't know if the pavement is actually under there or not.
Another example here on the left-hand side, I can see taillights in front of me, but I can't tell what that water's doing.
Yeah, it's just with the heavy rainfall, all you see is water. Later on, after the water's gone down, you can see where it's washed out, taken out the pavement, and if you try driving through it again, 6 inches of water will sweep a person off their feet. A foot of water will take the car off the road.
Looks like we have a question.
The question is it true that the sun can keep the storms more powerful?
Definitely.
Yes.
As a matter of fact, that's normal for us as we're watching tornadic storms, as they're going to occur late afternoon. We've got the most heat coming in because, again, that's part of that source of lift, and it keeps feeding that moisture into the storm system.
And typically, after the sun goes down, the storms weaken, spotters can go home. But that's typically.
Typically.
You can have tornadoes popping up any time of the night.
So we've got a video here for some nighttime spotting.
Okay, what you're looking at, or what you're not sure you're looking at, you can only see it when the tornado or the lightning strikes. Possibly some funnel, or maybe just scud. You don't know for sure. Because once it goes black, you can't see anything. That could be a wall cloud forming there. Very difficult to tell if there's rotation or not. And now everything's kind of changed. But you're seeing scud in there.
Another big threat that we have, hail. Let's look at a video of some hail.
$1,900.
Couple of good reference sizes there.
Excellent. Something nice to have along.
And another video here, in this case, another spotting hazard. Let's look at tornadoes.
We are good. The tornado cyclone is now moving overhead, but the motion of the tornado appears to still be to the right. Phil, pack it up. We got to move now. Absolutely. Stop what you are doing and throw the tripod in. Somebody shut that trunk. There is a lowering to the left, and that is coming right this way.
So Dave, looking back at that last one, you don't want to get too focused on that one tornado. Another one could drop down right next to you and bite you.
That's true. Skip's a very talented chaser, and yet that one was one that could easily have caused some problems.
Yes, you could hear the excitement when it's time to move.
And it looks like we have another question.
For night spotting, could spotlights, light bars, or something similar be used to light up the clouds good enough to see then?
Probably not. I've done a fair amount of night spotting. The only time I'm willing to go out is when you've got a very electrically active storm. Now, the interesting thing about that is that even then it's dangerous, but I will point out, though, that electrical activity means that there's liquid precipitation and frozen precipitation. Might not be hitting the ground, but they are in close contact to generate the static electricity. So there's a potential that you're going to put yourself in harm's way, not just from not being able to tell what you're looking at, but also from the hail that's pretty obviously in the air at least.
And an important thing about night spotting, the guys down in the operations center aren't aware of how dang dark it is out where you're at sitting in your car. So sometimes we have to have some communication back and forth that, yeah, maybe it's time to bring them in because it's just too dangerous out there.
Yep. The person most responsible for your safety is you. We're going to do our absolute best to keep you safe, but you're the one who's actually got your butt on the line. Critical information that we're going to look at reporting here. Number one, be sure to watch the storm for a few moments. Unless you have a tornado on the ground, you've got time to be looking at it and understand what it is you're looking at. Report exactly what you see and do it in an accurate and timely manner. If you've got uncertainty, express that uncertainty. It's okay if you're unsure about something. So what are we going to communicate? Who you are, what you see, when that event occurred, and where that event occurred.
So what are we going to report? You're sitting out there in the country, obviously, hey, we're going to report tornadoes. We also want to know about funnel clouds. Just to your spotting group, any wall clouds. If you're reporting to the Weather Service, they want to know especially about rotating clouds. But for our spotter group, if you report a wall cloud, that gets other eyes on it, so we can see where the things are actually occurring. You're going to report any wind damage or measured winds if you have an anemometer available, reporting wind speeds over 50 miles an hour. Hail, especially hail over 1 inch in size. The other thing is flash flooding or any water over the roads. We need to be reporting that so that the authorities know if they need to close off sections of roads or not. And then if you're aware of any fatalities or injuries, get those reported in.
And those can be reported, they don't have to happen in real time if you're not aware of them, but be sure to report them because that all goes back into the National Weather Service for those storm reports.
When it comes to reporting hail, we look at specific sizes. We don't report marble size hail because marbles vary. You can talk about pea size, which is about 1/4 of an inch. Better yet is penny, quarters, golf ball, tennis ball type of situation. Something we actually have a measurement on. If there's enough hail out there, we'll get an actual measurement with a ruler. Don't guess. Don't say lots of hail. And it doesn't matter, if you have hail out there, you measure the largest stones that are falling.
Reporting wind. You can report damage. You can report measured wind. Don't report estimated wind speeds. But definitely report damage to structures, downed power lines, trees that are snapped or uprooted, limbs that are down. If you get a chance to measure them safely, be sure to measure them as well. That helps to give an indication of how strong the storm or how strong the winds were after the fact.
And this is something we do quite often after a severe storm rolls through. We'll ask our remaining spotters as you drive back home or drive back to the base, check for damage, and report it back in then.
Be sure to report flooding. How deep is it, if you can tell? Is the water flowing or just ponding? What are the impacts? Do we have flooding of structures? Is the stream and river out of its banks? Are roads closed? How about minor street flooding and low water crossings? All of that matters. Most importantly, remember, turn around, don't drown. You don't know what's underneath the roadbed.
That's right. And beware of lookalikes. What we talked about before, the scary looking clouds. They're not attached to the updraft base. There may be rising motion, but no rotation. These could be scud clouds. What's the term, Dave, for scud?
Scattered cumulus under deck.
Good one.
The
Okay,
technical name for that would be cumulus fractus.
that's why you're smarter than I am. But always monitor the storm. Don't be confused by blowing dust, rain shafts. Know what part of the storm you're looking at. If you're looking at the updraft or the downdraft and the movement of the storm, so you're reporting correctly.
Let's look at some videos of some lookalikes.
Right here, we're looking at scud. It's very scary looking, but you're not seeing any rotation. If you just looked out the window, you saw this, you'd think, oh my gosh, there's a wall cloud with a tornado. But as we zoom in especially, boy, you can barely determine any upward motion, much less any rotation in the area. Pretty benign structure. Here again, we're watching what's happening as it moves through. What part of the storm we're looking at, the rain is behind us. So we're looking at a feature of the downdraft. Probably have shelf clouds up above. Very nasty looking. If you just looked out, you'd say, oh my gosh, that's a tornado hanging from a wall cloud. When in reality, it's just scud floating along.
So how do we report those things? Well, if you're working with a spotter group like Steele County SKYWARN, you want to submit those reports through your local net. Talk to each other. That's important. If you're not working with a group, you might be doing it, you can report online. There's storm reporting forums available on the National Weather Service website. You can use social media. You can use spotternetwork.org, another website, which has some great training as well.
That's right.
But you can utilize that one for making your storm reports.
Also notice you can email or your mobile apps such as MPing. You can go to the National Weather Service website that we talked about before. Underneath the hazardous weather, there will be a tab drop down that says hazardous weather reports or severe damage reports. You can also come over and report on Facebook or Twitter. Twitter is the preferred method because it's a live feed. They can see it as it goes through, and it's easier to disseminate to other people. Facebook, they may get it or it may be delayed. They may get it immediately or it may be tomorrow. Facebook is not necessarily reliable as a method for reporting storm damage. A great way to get photos and stuff in after the storm, but the primary one is Twitter.
Email is also a great one if you're looking at post-action damage. So you weren't there when it was happening, you're not reporting it in real time, but you want to report that damage that took place out someplace along the road.
So, again, we're looking at Facebook. You can follow the National Weather Service on Facebook. They will provide some updates. And on Twitter. These are some reports that have come in. Severe storm in southwestern Minnesota. The photo over here is actually the latest rendition of the Operations Center up at Chanhassen, the National Weather Service.
If we're looking at social media, one thing is watch out for hoaxes.
Tons of hoaxes on social media. These storms have been presented as they actually happen in one spot. I believe the one on the left is Nebraska.
That's in Nebraska. And yet it's been reported as if it was in Alberta, Australia, Israel, Hurricane Katrina, other parts of Minnesota. Untold various wrong locations.
People like to post scary pictures. Looking at the one here, this isn't even a tornado. It looks really wicked moving into a town. However, a person is standing on the ground level here, and the geography or the topography actually slopes down. This is just the updraft mesocyclone hanging down towards the ground level, and from the photographer's perspective, it looks like a tornado.
Sample reports. Great thing, to utilize if you're going to be doing hail. Love to have a ruler. You can you get a nice cheap ruler, you can throw it out on the ground as long as it's good big numbers. You don't even have to stick your head out there, except to pick it up later.
Stop by the dollar store.
There you go, buy a bunch of them. Otherwise, you can get gauges. There's a number of different ways. They're looking for the largest hailstone. But again, you'll notice on some of these hailstones here, those edges are not always smooth. So be careful. That's why we stay in vehicles.
Yeah, when the hail is actually coming down, you don't want to be running out there with the samples, looking for samples like they show on TV. Wait until it passes. It might be raining, but then you can go out and gather hailstones. If there are any significance, you can put them in a cooler, but at least get a photograph to send into the Weather Service. Here's a report on standing water. Filed, I believe this was on Facebook. Part of Main Street in Albert Lee typically goes underwater during heavy rain. So they made that notation that it wasn't something unusual, and they don't give any depths or anything, but it's something that typically goes underwater whenever they get more than an inch or two of rain.
Mm-hmm. So let's say that you've been out spotting, you're on your way back, and you come across this.
So, well, you call it in and report it.
Yes.
This one may be a little bit late because we actually have service trucks out there, but if you're coming in right after the storm, yeah, call in any damage like this, power poles down. If there are lines on the road, you may want to wait there for either police or service trucks to block off the road so that people aren't driving into it.
And it looks like we have a question.
Yes.
There's a couple of questions here. The first one is, what is the difference between a tornado and a mesocyclone?
It's a great question. Tornado, by definition, is a rapidly rotating column of air connected to either the wall cloud or the updraft base on the top and connected with the ground on the bottom. A mesocyclone is basically a lowering of the cloud base, and the wall cloud is a great example of that, and that is actually reaching down and touching the ground. It doesn't have the rapidly rotating speed. It may be moving, it may be turning, but it doesn't have the damage production that you see with the tornado.
Okay, and the second one, does film on a windshield like a UV tint help reduce hail damage?
I've no idea.
Well, I've heard of it being used, not so much on windshields, but on side windows to keep them from completely shattering out. It keeps, like in house glass, the film will keep it from shattering into a million pieces. It'll break, but it won't come in and hurt you.
That makes sense.
But as far as protecting everything, no.
And another one that popped up, what exactly does the mesoscale indicate?
Well, what you're talking about is the size of the storm. You're talking about a large portion or a large area. So when we talk about a mesoanalysis, we're talking about large portions of the atmosphere that are in motion. And then talking about the mesocyclone, you're talking about the large section of the storm that's actually rotating and is reached down to the ground. Does that help?
I guess that works. On to the next one.
Couple of sample reports on this one.
Well, what are we looking at here?
Well, first of all, you're looking at a rotating wall cloud. You can not tell that necessarily from a still photo, but we'll go with that. Possibly a funnel cloud. So again, what we're going to report in this case would be an example of, hey, I'm located 8 miles west of Wilmer at the intersection of Highway 40 and County Road 7. I'm watching a rotating wall cloud roughly 2 miles west of my location, with an area of enhanced rotation and possibly developing funnel cloud. I'll send another report if I see any further development.
And on the beginning of that, Dave, it's a matter of if we're reporting to our spotting group or if we're reporting to the National Weather Service. Then you definitely want to give your name and say, I'm a trained spotter, and not just someone guessing at scary looking clouds. It adds credibility to your report.
And the important again things that we're covering is who you are, where you are, what's happening, and when it's happening. And in this case, you're limiting it to what you see and what you know.
And report something like this. If it changes, I'll give you a further update.
So in this case, same storm, a few minutes later, we'll follow the same reporting guidelines as before. It's tough to call this one a tornado since we really don't see that much in way of debris. That could just be terrain though. So you could report, I'm located 8 miles west of Wilmer, intersection of Highway 40 and County Road 7 with an updated report. I'm viewing a well-defined funnel cloud descending more than halfway down to the ground. Now, I cannot see any visible debris at this time, but if rotation continues, a tornado looks very imminent.
In summary, we're getting towards the end. Storms are an incredibly dynamic process. It's always changing. We want to remember everything. Watch what we're looking at. Make sure we know what we're looking at. Understand the potential hazard of threat. We're watching the weather ahead of time so we know what's going to be happening, what to expect. Identify the parts of the storm, the updraft, the downdraft, know how they evolve. Maintain your situational awareness. Keep your heads on a swivel, watching all around. Ideally, have 2 people out spotting with you, or yourself and another person. And communicate. Let people know what's happening. If everything's still, as part of the spotter group, we'll check in with you if we haven't heard from you in a while. Maybe everything quiet, but we want to make sure you're out there. If you see something, call it in. We need to know what's happening out in the field. And remember, your safety is #1 priority. We try and look out for you in the operations center, but you have to be aware of what's going on. If something looks scary, call in. We'll verify it, or we'll tell you to get the heck out of the area.
So if you're looking for additional training, you might want to stop by steelecountySkywarn.org. We've got links to a lot of different training locations and websites. Spotter Network is a highly recommended one. Great testing. Before you can make reports on that, you actually have to go through their training certification.
It's excellent training. I don't remember, it's been a couple years since I did the Spotter Network training. It takes many hours. It's a lot more detailed than what we have here. Like I said, I've forgotten most of it or how long it takes. But it's very good training, very good explanation of the clouds, the cell structure, and everything. But there are other sources you can go to that we've got posted up here. Comet classes, you can go online to weather.gov and download the Storm Spotter Handbook. You can also go on YouTube. There's advanced spotter training. There's training available at Metro SKYWARN up in the Twin Cities, metroskywarn.org. The advanced spotter training and everything is available from the National Weather Service, Norman, Oklahoma.
So with that, we'll conclude our presentation today. We want to thank you very much for your participation, for taking the time to go through the training episode with us, but we also want to make sure that we thank you for your participation in spotting.
And don't forget to send in the information that's been posted up in the corner. Get it mailed in to Steele County SKYWARN at gmail.com so we can verify that you've attended the training tonight. We'll get you certified. There are links on Facebook, or you can go to Steele County Emergency Management under volunteers to figure out how to sign up for a badge if you want to be active in Steele County SKYWARN.
Thank you very much. I want to, are there any remaining questions out there that we need to deal with?
We're getting no nods.
Just a few thank yous from the participants watching.
Well, thank you for coming and joining us tonight. Being part of this, you wouldn't believe how much work is being put on, especially behind the scenes by Dan Petzinger. We have Tom and Bob back there. The amount of setup that goes into this, what looks like a simple presentation, has actually taken a lot of time and effort on volunteers.
but it's been a lot of fun.
Yes, it has.
Thank you, Jerry.
Yeah, thank you, Dave. And thank you to everyone participating here.